Hi everyone, I'm Josemary on behalf of GemScript, and today we are interviewing iGEM University of Rochester. So iGEM University of Rochester, can you tell us more about your project for iGEM 2023?
Yes, so our project is using a yeast and bacteria parallel culture system in 3D printed hydrogels to synthesize complex molecules, specifically plant-derived chemicals.
So can you tell
So
us,
basically we're gonna design a 3D printer. Okay, yeah. We're gonna design a 3D printer to print the hydrogels, and then we're gonna have the bacteria synthesize like an intermediate of the molecule. We're gonna use rosmarinic acid as a proof of concept, but basically it could be used for any other chemical. And then the yeast is supposed to pick up that intermediate and then synthesize the rosmarinic acid.
Yeah, and we're just using this model to see how we can implement this type of structure of co-culturing for future more complex molecules and show that the synbio aspect of this can be used in agricultural methods as well, instead of going through the whole process of purifying and harvesting more complex like medicinal plants. We could just synthesize it in the lab.
so can you tell us more about how you went about selecting your model organism for your proof of concept?
Do you want to?
I can do that. So basically we wanted like a chemical that is like plant derived, because we know that these are the most like complicated kind of molecules to synthesize, just because we need like to plant the plant and then like harvest it and then like extract the chemical from it. So, and we also needed a chemical that wasn't dangerous. So because we thought about like different like chemicals that would have medicinal uses, but we wouldn't really be allowed to synthesize that. So we wanted something that would be mainstream enough that we didn't need any extra authorization. So we decided rosmarinic acid. It also doesn't have a biosynthetic pathway that's too long or too complicated. So it could be done in the lab. And none of the intermediates are toxic to either yeast or bacteria. So it wouldn't really cause a problem.
And the benefit of using like the yeast and bacteria is that bacteria obviously grow a lot faster. And they're good with smaller molecules and can rapidly produce them. But when it comes to larger molecules that have a larger metabolitic like load on them, they are not as efficient. So that's why you split up between the bacteria and the yeast. And yeast are also better at handling more complex molecules and larger molecules. So while the bacteria kind of will quickly make intermediates, the yeast will do the finishing steps of modifying the final molecule to make the product.
And we chose to use E. coli and yeast since they're well-studied model organisms. So by putting their pros together, we can take advantage of more complex ideas like that.
So what type of impact do you think your project could have as far as different applications?
So we'd hope to apply this to plant-derived medicinal chemicals, just so we can impact like the price of pharmaceuticals, and also just like a lot quicker. We believe that you can apply this to most drugs, because they're still small enough molecules that the yeast can do it. It's just that the timeline of iGEM is obviously very short, and since we don't have a lot of wet lab time during the summer, we chose this smaller molecule.
It's also that with global warming, we're observing like a lot of issues with growing these plants for these plant-derived chemicals. So there's already like issues with like supply shortages of many like very like crucial plant-derived medicines. So this like kind of alternative to the plants would help prevent these shortages. And so our goal is to have this implemented in like factories or like, like so that it can be like scaled up and be used for industry.
Can you tell us more about the human practices portion of your project and how you're using this perhaps to educate others or examine the impacts it might have on the community?
So in terms of human practices, I know we are talking to a lot of farmers and how their current like rosemary production is, because rosemary is one of the plants that rosmarinic acid is derived from. As well, we're talking to like biomanufacturing companies and factories and seeing how their production line works. Our production process is through a 3D printer, primarily just to see how the hydrogels can be formed to allow the co-culture system to work. So we're just seeing how the experts in the fields do their processes, and we are gonna reach out to the customer base and see how their like questions can be better answered through our models. We're also gonna show our prototypes of the 3D printer model as well as the software to see how to better improve it and take feedback from people who don't know anything about our project and see how we can better implement those strategies to make our process more efficient. And then we're also talking to some high school students actually next week or the week after, and we're just teaching them about like how synthetic biology works and what like DNA is and like these simple biology questions so that they can be more interested in learning about the science themselves. So we're doing some other outreach as well, not just with the experts.
So the 3D printing aspect of your project is very unique. So can you tell us more about that and how your team decided to apply that into your proof of concept as well?
So the research that we based kind of our original project ideas off of was using hydrogels that were just extruded from syringes by hand. And so we kind of see this as a way you can do something very similar with the printer. Obviously, you can make more complex shapes though. So we want to see how the complex shapes of the hydrogel can actually improve the efficiency and speed of the diffusion of the intermediates to each like organism. And so that is why we chose our printer, just because the printers just have an ability to be way more exact than a human hand, especially with like extruding of these like higher viscosity materials like hydrogels.
And we're also making sure to like test different factors or ratios of different bioinks and seeing what is most like stable for like our uses. And so we're also using that as part of our hardware just to like test different bioinks, their viscosities, and like seeing whether the E. coli or yeast prefer one over the other and use that as our final model.
Are there any other unique details about your project you would like our audience to know?
Well, we think it's pretty important just because it's kind of a need right now. There's a need for the synthesis of these chemicals, and when we say plant-based chemicals, there's a lot of medicines that plant-based that can be like there's an anti-cancer drug that's used that's plant-based, morphine, a lot of very essential chemicals at the moment are plant-based, and there's a shortage of that. So we think our project can be like, with proper implementation, it could be crucial in helping prevent these shortages.
We're also doing some metabolic modeling just to see how a sort of complex pathway that is converging from an E. coli yeast into the overall yeast, making the rosmarinic acid at the end. So this type of biochemical pathway can be modeled. And so we're using that as a way to see if our production stops for some reason, what can we increase expression of, or what can we like add into our hydrogels to make it a more efficient process.
Well, iGEM University of Rochester, thank you so much for telling us more about your project for iGEM 2023. On behalf of GenScript, best of luck in the iGEM Jamboree and best of luck in our iGEM 2023 sponsorship competition.
Thank you. Thank you for having us.
Thank you.